Okay, let's begin. Last time we discussed the cosmic microwave background, which was an echo of the universe that we see today, dated to when the universe is about 380,000 years old. So now we'll discuss a much prior epoch. We'll discuss the first 3 minutes. The idea here is that there's a lot of inferential evidence we have about the early universe that we don't measure directly, we measure inferentially. The cosmic microwave background corresponds to when the universe first became transparent to radiation. Before that, because the universe is opaque to radiation, we can't view things directly. So we need to explain physics somewhat indirectly. But the evidence is rather compelling here. So if we consider the mean energy of a photon, we can compute this by computing the total energy density of the photons by the number density of the photons. And we know how to compute these things from the distribution with respect to the frequency. So the total energy density is the integral from 0 to infinity, d nu, 8 pi h over c cubed, nu cubed, e h nu over k Boltzmann t minus 1. And the number density is integral from 0 to infinity, d nu, 8 pi over c cubed, nu squared, e to the h nu over k Boltzmann t minus 1. So the expression in the integrand in the denominator, the expression in the integrand in the numerator differ by a factor of 1 over h nu, which is 1 over the energy of a single individual photon. So we see that if you compute the mean energy at the Planck time, this would roughly be the Planck energy, which is 10 to the 28th electron volts. And if you compute the mean energy today, this is 6 times 10 to the minus 4 electron volts. So the difference between this number and this number is rather easy to explain. We know the universe is expanding. So the first law tells us that dq is dE plus P dV. dq is the heat that flows in or out of the system. dE is a change in the energy. P is the pressure. dV is the volume. Working in a homogeneous universe, dq is 0. So dE by dt is minus P t dV by dt. So the energy is the energy density in the photons times the volume. And this is going to be alpha t to the 4th times the volume by the Steffen-Boltzmann law. The pressure is P gamma. And this is alpha t to the 4th over 3. Factor of 1/3 is here because working the radiation in the equation of state is that the pressure is 1/3 the energy density. So plugging these into this expression here, we have alpha 4t cubed dt times the volume plus t to the 4th dV dt. That's the left-hand side. This equals minus 1/3 alpha t to the 4th dV dt. And rearranging terms a bit, 1 over t dt dt is minus 1/3 1 over v dv dt, or d by dt logarithm of t is minus 1/3. You can do it this way. The volume is proportional to a cubed, where a is a scale factor. So this expression here is minus 1/3 a cubed times 3a squared dA dt. So plugging all this in and rearranging terms, d by dt logarithm of t is minus d by dt logarithm of a, and hence the temperature is proportional to the inverse of the scale factor. So consequently, it's not a surprise that the mean energy in a photon at a very early time, the mean energy in a photon today, differ by so much. That's just a statement the universe has expanded tremendously since the early time. So what this lets us conclude, this expression relating temperature to scale factor, is very early in the history of the universe. It was very hot and it was very dense. And the high temperatures turn out to mean that a lot of very interesting physics happened as a consequence of the interactions during that early time. And we'll see in this lecture that in this radiation-dominated phase, the first 5 minutes or so, the chemical elements were formed. So the topic here is Big Bang Nucleosynthesis. We'll try to understand this formation of chemistry as we know it. So let me set some notation. A nucleus contains Z greater than or equal to 1 protons and N greater than or equal to 0 neutrons. So protons have a charge +1, the neutrons are neutral, charge 0. We'll define a quantity A as Z plus N, and this is called the mass number. And we can identify an element as A element. The element is determined by Z. So for example, we'd write 1 hydrogen, 2 hydrogen, 3 hydrogen, 2 helium, 4 helium, etc. So the where'd my eraser go? The light elements, these isotopes, have names. So 1 hydrogen, we'll just call ordinary hydrogen. 2 hydrogen is called deuterium. 3 hydrogen is called tritium. Tritium turns out to be radioactive. We'll abbreviate 2 hydrogen often as D. And for helium, so these are elements with Z equals 1, and Z equals 2. We have helium. There's 4 helium, which is ordinary helium, and 3 helium, which is a rarer isotope. Should have been 3. At Z equals 3, we have lithium. At Z equals 4, we have beryllium. But in general, astrophysicists like to call all of the elements besides hydrogen and helium metals, irrespective of whether they're metallic or not. Okay, so we think of the ordinary hydrogen situation as a proton nucleus by itself, with perhaps an electron around it later. And we think of deuterium as a proton and a neutron in some kind of bound state. So a free proton, which is the same as one hydrogen, plus a neutron, forms deuterium, and it liberates 2.22 MeV of energy in forming deuterium. So the energy of the deuterium nucleus bound state is less than the energy of the proton and the neutron separately. So this 2.22 MeV, we'll call BD, is the binding energy. Of deuterium. And similarly, the other elements, their nuclei, have binding energies corresponding to the amount of energy liberated when you take that number of protons plus that number of neutrons and bring them together to form a nucleus. So it's interesting to plot the ratio of the binding energy to the atomic number, the mass number, versus the mass number. And you'll see in your notes that this yields a curve that peaks at E over A is approximately 8.8 MeV. And the isotopes that correspond to this peak are 56 iron and 62 nickel. So, let me try to see if I can reproduce this curve. Curve looks something like this. So the peak is around 8.8 MeV, but the 4 helium isotope is also rather large on its own. It's got the most binding energy per nucleon of the light elements. So the value there for B over A for helium. So for helium has a B over A of 7.07 mega electron volts. So it's the most tightly bound of the light nuclei. So nuclei that are more massive than 56 iron, they can release energy by nuclear fission. And isotopes that are less massive than 56 iron, they can form isotopes that are heavier and release energy that way as well. So if you're more massive than iron 56, release energy by fission. And if you're less massive, you can release energy by fusion. So fission is when we split into lighter nuclei. Famously, radium-238 fission is the power behind the atomic bomb. And in the process of fusion, we combine into heavier nuclei. The energy released by fusion might save the world if we ever get a fusion reactor. So, in Big Bang nucleosynthesis, fusion is into deuterium, then into for helium, and then into some of the heavier nuclei, the metals. So you'll notice the ratio BD, the binding energy deuterium, to Q, which we discussed last time, the binding energy of a proton with an electron, is 1.6 times 10 to the fifth. So first guess for what the temperature of nucleosynthesis might be is that it's this factor times the temperature for recombination. We discussed last time the temperature for recombination was about 3,740 Kelvin. So nucleosynthesis might be 1.6 times 10 to the fifth as T recombination, which is about 6 times 10 to the 8th Kelvin, which corresponds to a time of about 300 seconds. This estimate of T is slightly low, but it's not terribly wrong. The nucleosynthesis time really corresponds to the first 3 minutes, so we're off by about 120 seconds. Okay, a quantity which we'll find useful to define is Y, and Y, well, by P we'll call it, is the primordial helium fraction. So this is the density of 4 helium to the mass density of baryons. In the sun's atmosphere, y is 0.28. But for astronomical objects, we see the distant sky, y is about 0.24. So the difference between the helium fraction in these astronomical objects and the helium fraction in the sun's atmosphere is simply due to the fact the sun is not a first-generation star. So the sun was formed from gas that had been in stars previously that went supernova, and the production of energy by the stars, how the stars shine, creates some more helium. So that's why the helium concentration in the sun's atmosphere is higher than the helium concentration in these distant astronomical objects. A next useful thing to define is a quantity I'll call Qn. It's the difference between the rest energy of the neutron and the proton. And this works out to 1.29 megaelectron volts. So in particular, a free neutron is not stable. Neutron wants to decay into a proton plus an electron plus an anti-electron neutrino. The anti-electron neutrino is there in order to conserve electron number. Standard model, the proton's got plus charge, electron's got minus charge, so this whole right-hand side is neutral. The neutron was also neutral to begin with. The decay time is 890 seconds. So if we start off with N0 free neutrons, then after a time t, we have Nt is N0 times the exponential minus t over tau n neutrons. And the half-life T1/2, when Nt is 1/2 of N0, is equal to tau n log 2. Okay, so in comparison, MEC squared, Me is the mass of the electron, is 0.511 MeV. So this is a little more than twice that. So in this decay, we have the proton being 1.29 MeV lighter than the neutron, the electron being 0.511 MeV, and the rest of the energy is carried away by the kinematics of the particles involved in this process. So because of this decay time, when the universe is a few hours old, there are essentially no free neutrons left. All the neutrons that remain are bound up into nuclei. So a neutron which is bound up in a stable atomic nucleus is protected from decay. So that's how the neutrons survived this early epoch. Okay, so Big Bang nucleosynthesis is basically the race to bind up these free neutrons before they decay. So let's start very early. T is 0.1 seconds. The temperature back then was 3 times 10 to the 10th Kelvin. The mean energy of a photon back then was about 10 MeV, which is much, much bigger than 2 MeC squared. So as a result, we had photons forming electrons and positrons. So there's a pair creation of electrons and anti-electrons. And the neutrons and protons are in equilibrium. So neutron plus electron neutrino forms proton plus an electron, and neutron plus a positron forms proton plus an anti-electron neutrino. So these processes are going both ways at roughly the same rate, since the neutrons and the protons are at equilibrium. So at equilibrium, just an analogy to last week's discussion of the CMB, we have the following expressions. So the number density of the neutrons is Gn, that degeneracy factor, Mn kBt, 2 pi h bar squared to the 3/2 exponential minus Mn c squared for kBt. And Np similarly is Gp, Np, kBt, 2 pi h bar squared to the 3/2 exponential minus Np c squared for kBt. So these degeneracy factors, Gn and Gp, they're both 2. So the ratio Nn over Np is Mn over Np to the 3/2 exponential minus Mn minus Np c squared k Boltzmann T. So this ratio Mn over Np is about 1.002. The numerator here is Qn. We'll think about 1.002 is close enough to 1 for our purposes mostly. So when K Boltzmann T is much, much bigger than Qn, so the temperature here is much, much bigger than 1.5 times 10 to the 10 Kelvin, or T is much, much smaller than 1 second. The number density of neutrons equals the number density of protons, because this kBt in the denominator overwhelms the Qn in the numerator, and this exponential factor then is either the minus 0, so this exponential factor is essentially 1, and this ratio in front is essentially 1 as well. So once the temperature drops below that critical value, something very interesting happens. So T drops below 1.5 times 10 to the 10 Kelvin. After this point, the protons are strongly favored. So if we plot Nn over Np versus temperature, initially, when the protons and neutrons were in equilibrium, the ratio of the number densities was 1, and then it drops precipitously temperature we're discussing, it's called the freeze-out temperature. So after freeze-out, neutrons and the protons are no longer in equilibrium, and the reason is essentially because the universe becomes transparent to neutrinos around this temperature. So I wrote down a bunch of interactions earlier, and they all had these neutrinos or antineutrinos appearing in them. So we had N plus nu E going to P plus E, and N plus E plus going to P plus nu E bar. So when this equilibrium processes were happening, these neutrinos were interacting with the neutrons and the protons. Neutrino interactions happen by the weak force. So weak force is the force that's responsible for things like radioactive decay, for example. The weak force has a cross-section sigma that's proportional to the square of the temperature. So sigma weak is proportional to the temperature squared, and we can write, in fact, sigma W is 10 to the minus 47 meters squared, kBT over 1 MeV squared. So, in comparison, you look at, say, Thomson scattering and electromagnetism, sigma E is 6.65 times 10 to the 29 meters squared. So the cross-section here is much, much smaller than the cross-section here. Now we know the temperature is proportional to the inverse of the scale factor. We're also discussing very early times. So we're in a radiation-dominated phase of the history of the universe. And radiation domination tells us that the temperature is proportional to T to the minus a half, where sigma W, which is proportional to T squared, is scaling like the inverse of the time. So just as we saw with the CMB, the rate with which protons and neutrons interact with neutrinos and antineutrinos, this scales like the number density of the neutrinos times the speed of light times sigma w. The number density, this guy is falling like 1 over a cubed, because the universe is expanding. This is going like t to the minus 3 halves. Sigma w is going like t to the minus 1. So this rate is falling like t to the minus 5 halves. So a dot over a, the Hubble parameter, this guy is proportional to T inverse. So at some point, when gamma, the rate, is approximately the Hubble parameter, the neutrinos decouple. And the mean free path of the neutrino at this point effectively becomes infinite. When this happens, the consequence is the ratio n over np gets frozen. Okay. So nn over np is the exponential of minus qn over kb temperature at freeze out. And this is about 0.2. So kBt freeze out is about 0.8 mega electron volts, and T freeze out is about 9 times 10 to the 9 Kelvin. So T freeze out, the time that freeze out happens, leaves plenty of time for physics. So in particular, the ratio of neutrons to protons, there's 1 neutron for every 5 protons. And these neutrons are now decaying. And it's a race against time, because of this decay, to see how many of these neutrons can we put into nuclei. So, as an observation, due to the relative scarcity of neutrons compared to protons, Big Bang nucleosynthesis is inefficient. So we can view this as a race against the clock to bind neutrons in stable atoms so they don't decay. So, to sum up what we've done so far, we've noticed that very early in the history of the universe, the neutrons and the protons were in equilibrium. They were in equilibrium due to processes that are mediated by the weak nuclear force. The weak nuclear force in these processes involves neutrinos and antineutrinos. So these neutrinos were interacting with the protons and neutrons around them. But this doesn't last forever because the universe is expanding, the density of these neutrons is falling, and as the universe is cooling down in this process, we find that at some point the neutrinos stop interacting. So they decouple. This happens when the rate of the interaction equals the Hubble parameter. At that time, the ratio of neutrons to protons gets fixed. It's fixed at about 0.2, so 1 neutron for every 5 protons. We know that neutrons decay, and the point of Big Bang nucleosynthesis is to put them in nuclei that are stable. So, how do we do this? So we can imagine 2 protons combining to form a deuterium nucleus plus a positron. So deuterium is a proton-neutron bound state, so it has 1 proton here, so it has charge 1. There's charge 2 over here, so the positron's here for conservation of charge. And there's a neutrino here for conservation of lepton number. This guy involves the weak force, and as we've seen, because it involves a neutrino, this is becoming rarer and rarer as the universe is expanding. Contrariwise, you can form a deuterium nucleus, taking a proton, combining it with a neutron directly. This gives us deuterium plus some energy. This involves the strong force. Or if you like, QCD, quantum chromodynamics. So the latter process, this second process, is the one that's dominant in the early universe. Because of decoupling, the former process is disfavored. But the former process is how the sun shines. Protons combine or fused into deuterium. And this can happen because the sun is in a state of hydrostatic equilibrium, whereas the early universe is out of equilibrium. We'll see the importance of equilibrium in addressing one other puzzle, which is somewhat hidden in this entire discussion, that we'll return to later. Okay, so in the early universe, the temperature is dropping like T to the -1/2, and the number density of baryons is dropping like T to the -3/2, and this is just due to the expansion. Okay, so what's the best we can hope for in Big Bang nucleosynthesis? The best we can hope for, well, NN over NP, that ratio was about 1/5. So if we take 2 neutrons and 10 protons, we'll get 4 helium, which contains proton, proton, neutron, neutron in the nucleus. So there are 8 protons left over. So Y max then is 4/12. So there are 4 nucleons that are bound into helium, and there are 12 nucleons in total. This is 1/3. So if so the ratio NN to NP, this is somewhere between 0 and 1, we'll call it F. It turns out Y max will be 2F over 1 plus F. And we have, in our observed universe, YP is 0.24, which is less than Y max, which set was 0.33. So the reason YP, so several reasons why YP is less than Y max. One reason is the spontaneous decay of neutrons. So remember, they're unstable and they're decaying to protons. So this lowers this fraction Y. Neutrons also are bound up into deuterium, tritium, 3 helium, and metals. And as a result, not everything in the universe turns out to be just for helium. So those are the 2 reasons why we don't max out this Y. Okay, so we'll next discuss the synthesis of deuterium, and then we'll talk about how the helium forms. So this ratio, Nn over Np, equals 0.2. This gets fixed to freeze out, so about 2 seconds. And after that, the photons are strongly coupled to the protons and neutrons. So we have proton plus neutron forming deuterium plus gamma. And the binding energy in deuterium is Mn plus Mp minus Md times c squared. And this is about 2.22 mega electron volts. So last week we discussed protons plus electrons forming hydrogen plus photons. Here the relevant parameter was Q, and this was 13.6 electron volts. So these 2 numbers, they differ by a factor of 160,000. But it's the same physics at the end of the day. So we're going to use the Saha equation again to evaluate what's happening in deuterium synthesis. So the Saha equation, which we derived last time, tells us that NH over NP Ne is Me K Boltzmann T 2 pi h bar squared to the minus 3/2 exponential Q over K Boltzmann T. So the analogous equation, this time, is the ratio of deuterium number density to the ratio of the proton number density, neutron number density is GD, GP, Gn, we'll use the degeneracy factors, MD, Mn, MP, to the 3/2 KBT over 2 pi h bar, the minus 3/2 exponential BD over K Boltzmann T. So MP is approximately the same as Mn, which is approximately MD divided by 2. GD, the degeneracy factor for deuterium, it turns out, is 3. And the degeneracy factors for protons and neutrons was 2. And this is just due to the spins. So ND over NP and N, plugging everything in, is 6 Mn KBT over 2 pi h bar squared, the minus 3/2 exponential BD over K Boltzmann T. So deuterium is favored as the universe cools. So KBT goes to 0, this exponential blows up, and this means the number density of deuterium increases. Whereas protons and neutrons, they're favored in the opposite limit. Where KBT is large. T nucleosynthesis is the temperature at which the ratio of deuterium to neutrons is 1. So half of the free neutrons have been captured at this point. Okay, so rearranging this expression here, ND over NN is 6 NP Mn K Boltzmann T 2 pi h bar squared minus 3/2 E to BD over K Boltzmann T. So we saw that 5/6 of the baryons were unbound protons. So the same thing as saying, initially we had one free neutron for every 5 protons. So NP then is 5/6 N baryons, which we saw last time was 5/6 times eta times N gamma. And we can compute N gamma from the photon black body spectrum. It's the same as the recombination story from last week. N gamma is 0.243 K Boltzmann T over hc cubed. And we derived this from the photon black body spectrum. So we can plug this in to the expression above. When we do that, we realize the following. We see that ND over NN is 6.5 eta K Boltzmann T over MN C squared to the 3/2 e to the BD over K Boltzmann T. And we put eta, this is model dependent, to 5.5 times 10 to the minus 10. We set ND over NN equal to 1, and we solve for T nucleosynthesis, and we find this is 7.6 times 10 to the 8 Kelvin, which corresponds to a time of about 200 seconds. So when we say nucleosynthesis takes place in the first 3 minutes, this is where the first 3 minutes are derived. Now, NN over NP is changing as a function of time. So after 200 seconds, we've lost a lot of these initial neutrons just due to decay. So canceling units, etc. This leaves us with e to the minus 200 over 890. And there are initially 5 protons plus 1 neutron minus the exponential minus 200 over 890. So the expression here is 0.8, the number density of neutrons is falling, the number density of protons is increasing, over 5.2. So we had 1 to 5 before, 0.8 over 5.2 now. This is 0.15. So we're down from 1/5 to 3/20. And this means that Y max is reduced from 1/3, which was assuming no decay at all, down to 0.27. So instead of 0.27, we end up getting 0.24. So we lose even more due to the other effects that I mentioned. The neutrons are still consistently decaying. The neutrons are also getting bound up into what comes after deuterium. Okay, so what does come after deuterium? We notice there are other isotopes of hydrogen, and we noticed it was helium, and we noticed there were a bunch of metals. So after deuterium, we have deuterium plus a proton, giving us three helium plus a photon. So we have here a proton and a neutron. Here we've got two protons and a neutron. So that's a three helium isotope. We can also have deuterium plus a neutron, giving us three hydrogen plus a photon. So here, again, we have proton and neutron plus proton, giving us proton and two neutrons. So three hydrogen is unstable. It decays to three helium plus electron plus an anti-electron neutrino. But the decay time is 18 years, because the decay time is much, much longer than 5 minutes. It's basically stable during Big Bang nucleosynthesis. Okay, so now we have deuterium combining with protons and neutrons. We can also have deuterium combining with itself. So two deuteriums can get together and form four helium plus protons. Two deuteriums can form three hydrogen plus an extra proton, and two deuteriums can form three helium plus an extra neutron. It turns out that these guys are more likely to happen than the first. Finally, we can have three hydrogen plus a proton, forming four helium plus a proton. Three hydrogen, three helium plus a neutron, forming four helium plus a photon. Three hydrogen plus deuterium, forming four helium plus a neutron. Three helium plus deuterium, forming four helium plus a proton. So none of these interactions involve neutrinos, so they're mediated by the strong force, by QCD. So you have large cross sections and large reaction rates. So once nucleosynthesis begins, deuterium is rapidly converted into, and also three hydrogen and three helium are all rapidly converted into four helium. And four helium is the most tightly bound nucleus of the nuclei around it. So as a result, when four helium forms, it tends to stay stable. Okay, there are no stable nuclei with atomic number equals 5. And the processes that give heavier elements are like so. So because there's no stable nucleus with nothing with A equals 5, so 4 helium doesn't by itself combine with a proton or a neutron. Rather, we have 4 helium plus deuterium forming 6 lithium plus a proton, 4 helium plus 3 helium, forming 7 beryllium plus a photon, 4 helium plus 3 hydrogen, forming 7 lithium plus a photon, and 4 helium plus 4 helium, forming 8 beryllium plus a photon. So 8 beryllium is unstable, and it breaks up into 4 helium plus 4 helium again in about 10 to the minus 16 seconds. The fusion into these heavier nuclei is much less rapid than helium formation in the first place. So after about 10 minutes, Big Bang nucleosynthesis is long over. And nearly all baryons are in the form of single hydrogen atoms, single hydrogen nuclei, or helium. There's small amounts of deuterium, 3 hydrogen, and 3 helium left over. And trace amounts of heavier metals, 6 lithium, 7 lithium, and 7 beryllium. So the yields of these other elements, they depend on inputs, and they're model dependent if you're trying to model this theoretically compared to data. It also depends strongly on eta. So if eta was 10 to the minus 12, yp will be less than 0.01. If eta was like 10 to the minus 7, yp would equal y max. So to determine eta, we need to measure the primordial densities of these metals. The 4 helium fraction is relatively constant. In these models, but deuterium, 3 helium, and the metals are what we use to constrain the models. And they're the key to figuring out eta, which, remember, is the ratio between photons to electrons. Now the problem with making these measurements directly is deuterium is destroyed in stars. The fusion processes kill off much of this deuterium. So we look to the interstellar medium, and we look to other places that are primordial in character, distant parts of the sky. The spectra of distant quasars offer our best estimate, and d over h is 3 plus or minus 0.4 times 10 to the minus 5. And eta is 5.5 plus or minus 0.5 times 10 to the minus 10. Okay, so I've been talking a lot in this lecture about baryons. I've also mentioned electrons and positrons on roughly an equal footing in these various discussions. So a natural question to ask is, what about the antibaryons? Why are we just thinking about baryons? And this leads us to also ask, why is there stuff today made of matter rather than antimatter? As far as the laws of physics go, so far as we've seen them discussed, there seems to be, it could have gone the other way. What made nature prefer matter to antimatter? Since everything we see is made of matter. Indeed, this is not a local statement, but there's an interface between matter and antimatter. We detect this. So that's one mystery. A second mystery is, why is eta what it is? So why are photons preferred so strongly over baryons? And we'd like to make sense of these inequalities in the number density of things. So number density of antibaryons is much, much less than the number density of baryons, which is much, much less than the number density of photons. So we have two photons. These combine to form a quark and an antiquark. So quarks and antiquarks should be equally prevalent, and the neutrons and the protons we can regard as bound states of these quarks, and the antineutrons and the antiprotons are bound states of the antiquarks. Now, if there's a quantity delta Q, which is NQ minus NQ bar, so the number density of quarks minus the density of antiquarks, divided by NQ plus NQ bar for normalization, this is much, much less than 1, then the quarks are slightly preferred over the antiquarks. Okay? So, how many quarks, what is this overcounting, what is this overdensity of quarks necessary in order to form a universe in which we have some quarks left over with lots and lots of photons? So the reverse process, the quark and the antiquark, they annihilate and give us a bunch of photons, and these photons are accounting for this and gamma. So we can imagine a process in which the following occurs. We have quarks and antiquarks annihilating to form these photons. So lots of photons that arise from these annihilations, but because NQ is slightly bigger than NQ bar, at the end of these annihilations, some quarks are left over. And these leftover quarks form the baryons. So why would it be that the number density of quarks is slightly larger than the number density of antiquarks? So this was studied by the Soviet physicist Sakharov. Sakharov noted certain conditions necessary for Big Bang nucleosynthesis. So the Sakharov conditions are, first, baryon number violation. So there are more quarks than antiquarks, is what this means. But we also need other symmetries to be violated. We need C symmetry violation. So C stands for charge. It means that positively charged particles and negatively charged particles are treated slightly differently under some fundamental interactions. And also CP symmetry violation. So P here stands for parity. So particles with one parity are treated slightly differently than particles with the other parity. These interactions produce more baryons than antibaryons. And the third requirement is that all these interactions, they take place out of thermal equilibrium. And we need all of these things to happen in order to account for this slight difference in the number density of quarks and antiquarks. This slight difference yields the universe that we see and the matter within it. So how slight a difference are we talking? If we have 10 to the 9 quarks and 10 to the 9 minus 3 antiquarks. So in every billion quarks, there are a billion minus 3 antiquarks. This annihilation leaves 3 quarks left over. Surrounded by 2 billion photons. And that's the kind of difference we need to see in order for the universe to be as we observe it. So the differences are tiny, and there needs to be some physics to explain these differences, and these are the conditions. Now, baryon number violation is predicted by physics beyond the standard model. So BSM physics. But to date, we have not seen in an experiment any physics or any evidence for physics beyond the standard model. So I'm thinking about things like grand unification, supersymmetry. All of these things are physics that are potentially there at an energy threshold we haven't been able to measure yet, but we can easily construct theories that enjoy this property that baryon number is violated. CP violation by itself and C violation by itself, these exist within the Standard Model. However, there isn't enough of this within the Standard Model to account for these differences. So, again, this points to the existence of some new physics around the corner beyond the Standard Model to require these conditions to be satisfied. So the challenge presented by Big Bang Nucleosynthesis is that there are new aspects of particle physics for us to discover. This is good news. There's new physics to understand. In this area, theoretical discoveries, models, the description of what's happening in nature is helped by experiment. So the hope is that future accelerators will be able to shed light on some beyond the Standard Model physics in order for us to make some sense out of the story here. As well, beyond the Standard Model physics presents candidates for particles that might be dark matter, and we've seen the necessity for dark matter in our discussions earlier. So this is a good theoretical hope for fixing some confusions we still have about the early universe. This is a good thing in that we have the opportunity to learn something by studying these sorts of problems further. So that's sort of a short summary then of Big Bang nucleosynthesis. So physics that took 5 minutes or so took considerably longer than that to even outline. But there's quite a bit left to understand, and you'll start playing with some of this in the exercises. So I'll stop there.